This is the third part of the series, how to put together a simulation of a dynamic system in Rhino, Grasshopper, and Python. In this part, we will introduce geometry in the form of curves or polyline in Rhino, aimed at influencing the Boid's behavior within a Boid simulation. We will begin with the Grasshopper definition created in part 1 in this radio series to move 5 Boids over time. Similar to part 2, we will insert additional processes between the node creating the Boid instances and the node to run the move function within each Boid. In Grasshopper, we will first prototype what we will be coding in Python before coding it. We will be using standard Grasshopper nodes for this prototype. We will introduce a number of curves or polylines in Rhino. Find the closest points from a set of curves within a specified range for each Boid, and use the relative position between the Boid and the geometry to influence the direction of each Boid. And finally, combined with other Boid steering behavior influenced by neighboring Boids, which we looked at previously in part 2. We will start with one Boid instance to keep it simple, so we can see what is happening as we define the logic, as we prototype this specific behavior. To do this, we will make one line geometry and reference it in the inputs for the Boid system. Now let's create 2 curves in Rhino. And create a reference to them in Grasshopper. Next, we will extract the points and vectors from our Boid instances. For this purpose, we can reuse the node which we previously made in part 1 to obtain the position and vector for the Boid instances. We will use the standard Grasshopper node curve, closest points, to find the closest point on a curved object from an input point. Now let's visualize it by joining the position of the Boid and the resulting closest points. Notice we have 2 closest points on 2 separate curves, one for each curve. And the closest point node also provides associated distances between the closest point on curve and the input points. Next, we will find the closest point from all the closest points. An easy way to do this in Grasshopper is to sort the list based on the distance and the associated points. And now if we identify the first item, what we find here is the closest point, where the numerical value of the distance is the lowest. Next, we will check to see if the closest point is within a specified range as a variable that we can modify. To do this, we use the Grasshopper node smaller than. And we will find the closest distance. And we will create a slider to specify the range. We can visualize the range with a circle. And we will select the points using the true or false pattern from the numeric comparison. We can highlight these closest points within the specified range with a circle. And now you can see when the points disappear when it's outside the specific range. At this point, we have the closest point between the input point and the set of curves. Within the range of a specified number. We are ready to construct a vector to influence the direction of the Boid. Visualize it using a vector display. And you can see we have a vector from the closest point to the current position of the Boid. Now we will use this vector to influence the direction of travel. We will add the vector from the closest point to the current position to the direction of the current Boid. And let's visualize it with a vector display. We can control the influence by adjusting the magnitude and amplitude of this vector from the closest point to the Boid position. In this example, we will unitize both of the vectors. When we unitize, sometimes called normalize a vector, we keep the direction, but set its magnitude to 1 unit. And we can set a specific value for the vector from the closest point to the Boid position by multiplying the unit vector. This is the point where we can weight the influence vector as a function of distance. For example, a greater influence when the Boid is closer to the curve. But we will not go into that to keep it simple in this tutorial. And here we will modify the amplitude of the resulting vector. To a predefined length. Now we have prototyped the intended behavior visually. We will move on to code this in a GH Python node, which we will rename as avoid py, short for Python. We will have x for the Boid instances, and we will add an input CRVS for curves, and we will change the type hint to curve and list access. Now let's open up the code editor and begin first by printing X to see what we are getting. Here is the Boid instance, and if we print CRVS for the curves, we expect 2 curve objects in a list. Now the first thing I'm going to do is to import Rhino geometry as RG. And we will look at using this variable Boid as X. So when we refer to Boid, it's easier. And we will assign a new variable within the Boid instance, boid.avoid, and we will add a new vector, assign a new vector to this variable. And the next thing I'm going to do is to bring the curve closest points node into Python here. GH-Python has a helper library. Components as GH-comp, which is a shorthand for this library. Now, what I'm going to do is to use GH-comp for the Grasshopper components exposed by GH-Python, and we will find curve closest points here. So we will supply a point and a curve. Now the point is Boid position. And for the curve, we will run a for loop to go through all the curves. And each of the curve will be named CRV. And we can obtain some results from executing this command. Let's test it. So what we can see here, we're printing X, which is the Boid instances, the curves, which is the curves that we referenced in. And if we look further down, we have the results going through each of the curve objects, the distance, parameter, and the point. The next step in code, we will deviate a little bit from the prototype that we made earlier, but to obtain the same outcome. So we have the curve closest point here, and we want to be able to obtain the closest point within the prototype. And we are going to look at how we can find the closest point amongst multiple curves. Instead of sorting the distance and the associated points from curve closest points and using the node to find whether the point is within a specified range, we will create 2 variables within the Python script. Closest distance and closest point. And we will assign none to closest point, and we will create a new input called SD for search distance. and we will relate the slider into search distance and assign it to the closest distance initially. Now, because we are taking each curve one by one, and we can find the closest point here, let's assign a variable to the result. And let's find the distance from the closest point result and compare it with the closest distance, which is initially set as SD, the maximum distance that we want to search for. And if we make an if condition statement, if the closest point distance is smaller or equal to the closest distance, we will set the closest distance as the current closest point distance. And we found a closest point so far, which is cpoc.points. And what we're doing here is that because we are going through the curves one by one, the closest distance and closest point will update, and the ones that are greater, the distance that are greater than the previous one, for example, will not be updated. And at this point, if we print closest points, we should get the closest points. However, if the range is lower than our search radius, we will get none, which is what we have assigned as closest point initially, because none of the closest points distance satisfy this criteria. Now that we have the closest point, and we know that sometimes we won't get any result because none of the closest points satisfy or lies within the specified range, we can supply an if statement to say if there are closest points found, we will do something with it. And for this purpose, we will look at how to adjust the avoid vector and create the vector from this point. If we can find a vector here, which is, we'll be looking for this vector from the closest point to the current Boid position. So let's use the Boid position here, and if we minus the closest point from the Boid position, we can get this vector here. And similar to what we prototyped earlier, we are going to unitize it. And we will provide a weight to adjust this vector, which is this one here. And I'm going to add a new input called W, which is the same as what we use in the code. And let's bring this connection up. Now we can check the output of the vector avoid if we assign this to one of the outputs within a Python node. So for example, what we can do here is to say A is the Boid position and B is Boid.avoid. I spell it correctly. And we add a new output and a vector display. And we need to run it. Which is to the same direction as what we have at this point. Now we are ready to use the avoid vector to influence the direction. We will start by creating a new Python node, and we call it combine, similar to what we did in the previous part. And we will obtain the x, which is the Boid's instance, and we will make this an input simply to make it run based on the upstream dependencies. And we will add a new output here. We can now disable this or hide the previous geometry, and we will link it to run. And now if we add this to combine py node, if we print x, we should be getting the instances, and if we print x.avoid, which is the vector that we defined in here, and we have computed based on the nearest closest point on a set of geometries, we should be getting a vector within this variable. And what we want to do here is to take the direction of the Boid, similar to what we have prototype here. We will unitize it, and we will add the avoid vector to this direction. And we will set the magnitude, or to amplify the vector, first to unitize it, and we will set the direction as 5 units. And we will output x as a. So a, the output a is equal to x. At this point, we are now ready to attach what we have done so far to move, draw, and visualize as the complete process that we can iterate over time steps. So let's close the editor for both avoid and combine, and we will connect the output here with move. And to run the process over multiple time steps, again, we will need to relocate the button here and the trigger. Let's delete this. And let's rearrange some of our nodes so that we can see clearly where it is. So far we have created some instances of the Boids here. So this is the setup, and this is the beginning of the process. So we're going to compute the avoid vector based on some curves, the search radius, and we have specified a specific weighting for this vector of influences. and we have combined it with that is to add the influence vector with the current direction of the Boid, and we will move it, which is basically the point, the position of the Boid plus the vector, the direction of the Boid. And the process that we wish to iterate is the ones that I have selected here. So it begins with the avoid py, and very similar to what we have done in the previous part. We will add the run node or run input here, and we will add the trigger as a button to trigger this process. So now it has, I think some of the is somewhere here because the node has executed quite a few times. Let's first hide the ones that we have prototype, or actually disable this script here. We will need some of this if we trace the orange line, which is the search distance and the weight for the influence vector. Now let's reset it and let's try running it. Okay. One thing we might want to do is to use the recorded node to visualize the trajectory of our Boid instance. So let's try to build it here, and let's draw a polyline. Reset, and let's run it. So you can see how the Boid trajectory runs. Let's try different values for the weighting for the influence vector. So for example, let's lower this to 0.2, and let's reset everything here, and also activate the recording. Now let's set it to run. You can see we can get a different influence vector and outcomes. Now let's try to run it for multiple Boids. This is a slightly different setup to what we had before, which is basically different sets of initial condition and different sets of curves. And we will add a trigger here and specify a specific time interval for the process to run. We can now combine it with the exercise that we did in part 2 with the Boid's behavior for alignment, cohesion, and separation. We will make a copy of the alignment, cohesion, and separation process and the associated sliders into our new file. We will now disable this combine node and edit the combine node from the separation, cohesion, and alignment to include the vector avoid. And we will reconnect some of the pieces here. And we don't need the trigger. We can connect the boolean here so that we can run all the processes when we click on the button or trigger it at specific time interval. And we will add the influence of the avoid vector within this combined node. Simply by adding this line here, direction plus or minus plus or equals, which is the shorthand for equals x direction plus x dot avoid. X is the Boid instance. We will use the shorthand for now. Right. And we will reconnect A with X. Now let's run it. As an extra note, it is possible to run what we have created in this series at a much greater speed. This is an example where I have optimized the function within the code, and where we can look at how the dynamic system responds to changes in near real time. This can be a subject of a future video.